Peace. Works now? Okay.
To do a little outline about what we're going to be talking about. First, we're going to talk about why we care about walkability, our motivation for studying it, then why we created a new model, how currently our model scores walkability, and what we accomplished this semester and looking forward. So why do we care about walkability? First of all, we kind of got interested because during COVID, a lot of studies and research started tying walkability to different health patterns, specifically mental health, physical health, and even equity. And overall, walkability can be a benefit to urban planning, public health, and sustainability, like I mentioned, and support healthier lifestyles and better communities. Now I'm going to hand it off to Lucy to talk a little bit about the current competitor.
So WalkScore is the current status quo for walkability, and it calculates walkability by measuring proximity to amenities, but the actual methodology is proprietary. And sometimes
I went backwards, yeah.
And sometimes WalkScore can get it wrong. As you can see here, this area has a WalkScore of 80 out of 100, which is incredibly walkable. But when you look at it at Google Maps Street View, you see that it doesn't really deserve that score of 80. So that led us to identify a gap where new innovation can come in and create a better walk score that basically takes into account additional factors. And that's where our pedestrian environment index comes in. And I'll hand it off to Mason.
Yeah, so a couple semesters ago, we found this score called PEI. It was based off a paper from the University of Chicago. So I'll kind of go into what that original PEI is and kind of how we implemented it. So first, the main data source that we used was OpenStreetMaps and the census. So we were able to collect data from those and implement PEI. Yeah, as you can see here. And so PEI is split into 4 sub-indices. So the first one is population density. This is just a basic population density of, basically we went by census tracts. So we just found the area of the census tract and then the population, and then just found the population density. The next one, a little different, just the same sort of idea, is commercial density. So we queried OSM for all like sort of amenities you can think of, like restaurants, cafes, schools, cinemas. And then we essentially found the density that. And then another important one was land use diversity. So we used this idea of entropy, which is basically just like kind of the randomness, like how many different types of land use there are in an area. So we found, again, using OSM, finding different types of land use and kind of finding the area using that formula right there. And then the last one, also a kind of density centered index. This one, similar to the rest, but instead of population or commercial, this one uses sort of the intersections of roads. So it's kind of like the more intersections there are, the more intersection nodes there will be, so a higher density. And then we normalized all these sub-indices across different timestamps or different time periods, so we can compare them across years and across different metrics. So we did normalize, and then we combined them together into sort of this aggregate PEI score, which you can see here. So that was the old PEI metric, but we felt like it was adding a couple things or missing a couple things. So we wanted to add additional sub-indices to kind of create a better, sort of more complex and more aggregate score.
Yeah, so this semester I worked on refining my road safety index, or RSI, and basically it sets out to quantify how walkable an area is by looking at how likely individuals are to have social interactions based on how safe it is to walk on the roads in the areas. And one of the challenges I was addressing was just the lack of road speed limit data from OpenStreetMaps. Originally, I wanted to conduct policy research into every single state's legal documentation with regards to how they were setting their specific speed limits. However, I soon realized that some states really lack this comprehensive documentation, which potentially could make my data inaccurate. So this semester, I decided to take more of a federal approach. So I found federal guidelines that outline how we can create speed limits for every single state and apply that to my calculations. And that works because my model is more so interested in the relative safety scores of each census tract rather than the absolute scores. Another thing that I worked on this semester was addressing the falsely inflated safety scores in rural areas. As you can see here, that is Joshua Tree National Park, which is incredibly rural, but my RSI really gives it a really high walkability score, but that just is not true. And the reason this is because it has a really low road density, and just through my methodology, it just naturally will have a higher score. So I really wanted it to more so focus on the question of how safe is this track for people who walk here, and I thought the best way to do that was to weigh my original calculations by the census tract's population density. And as you can see here, these are some of the changes that I found. And the census tract at the top is the one with the biggest increase, and the one at the bottom is the one with the biggest decrease. The biggest increase is one where there's an intersection of a lot of highways, but there are still roads that are walkable and there are sidewalks on those roads. So it increased to not a super high score, but one that's a little bit higher than originally. And the one with the biggest decrease is one with where there's basically no roads there, no one living there. It's just the golf club, so not much social interaction going on there.
Okay. So last semester, I also added a sub-index called PEI to the social green space index, or this was social green space was my index that I added to PEI. Overall, the motivation was to see if areas could be more walkable if they contained more social outdoor spaces. It is computed as a ratio of area of all the green space added together over the total area of a tract. You can also see my test case of Atlanta on this slide, and this brings me to my application of the index this semester now. First, I edited and validated OSM query tags by sourcing them from peer-reviewed research instead of my own discretion. I also validated my overlay function, as with the visualization's contrast. I was uncertain if it was working correctly. It was tested and found correct. Third, I was worried about efficiency, but it was resolved as last semester, the amount of time it took to compile Atlanta took a concerning amount in relation to the fact that we were looking at data from nationwide and potentially more. Now to get into my limitations. Overall, this semester, after we queried OSM data nationwide in the social green space index, you can see that especially in places like Massachusetts, the state itself has incredibly comprehensive data, especially when compared with the state to the left, like Wyoming. So because we're using OSM data, it's naturally limited by what people are inputting into it. You can tell that people have inputted a lot of data into Massachusetts and not as much as Wyoming. So even though I validated different functions like overlay, overall, the index itself still is limited by the amount of data that it can put through it. And then also you can say that there's also a park delineation limitation because there are fluctuating patterns as a result of inconsistent inputs of the boundaries of the parks that my green space index is calculated on. So overall, the green space works as intended, the data limits it, and I'll be sure to note this limitation as we continue this project.
Yeah, and then another index we added that I created was the bike index or bikeability index. So similar to other indices that kind of focus on, density, we kind of did a similar approach here where we were able to query OSM, as you can see on the top right, for sort of like bicycle tracks or bicycle lanes. And so we found all those within a census tract, but then important thing we did was weighted them differently. So for example, if you have a separate bike lane versus like a shared bike lane or a painted bike lane, one is more safe than the other. So bike lanes that were separate or painted were weighted more than, bike lanes that were shared. So that was an important delineation. And basically we found the total length of bicycle lanes or bicycle infrastructure within a tract, and then just divided it by the area, sort of this density idea. And so you can see for Atlanta, the Atlanta area, sort of in the bottom right. And then another important index that we did previous semesters that I'll just talk about quickly was this idea of a public transport index. So this one was based on an index created from London, and essentially close to the other ones, but a little different. This idea of like how many transit stops or how many, bus stops are within an area. So this idea of density with a little difference, meaning that we take into account sort of how often the bus comes there. So that was used from transit stop data from local transit authorities. That's all aggregated on a website. So we got that, and that kind of like differentiates sort of, even if a bus stop is nearby, if it takes long to wait, then you have to account for that. So yeah, we had this index as well. And then if you could click on the link, I'd like to give a quick demo, just kind of share everything we did. Either you can control it or I can come over there.
Yeah, where should I go?
Mess around, and I'll tell you what tools to mess with. So yeah, as you can see, an important thing we did this semester was actually aggregate all of our data together across 3 timestamps, 2013, 2017, 2022. And we've always had the data here, but we were never able to visualize it properly or put it out somewhere where everyone could look at. So that's what we did this semester. So you can choose the year, you can swipe across different PEI metrics. And then an important thing we have the original PEI, which is what you're seeing now, kind of swiping across different years, but you can change the overlay, yeah, of course, to different years. And then you can also change, if you go to PEI original, you can kind of see, you can view R3 or R4 new indices or all 8 of them combined. And then you can also look at each independent index. So there's a couple different tools here to kind of, for us to use as the researchers kind of to tell what's going on, but also for anyone who's just curious.
Mhm.
So yeah, that's the website.
Awesome. Sorry, I need to find, sorry, but there's this.
Should be the third tab.
Yeah.
And then one last important thing we did.
Yeah, so they're mentioning all these great indices that we developed to measure different things, whether it's like social mobility or walkability or various things. And that's where like SMUR lives. And then we're also working with a researcher at Emory who was looking into mental health effects. He's a psychiatrist. And he's curious about how geolinked mental health data correlates with these different metrics we're developing. But linking them together is the difficult part. So I kind of lived in this plus space this whole semester in order to combine those metrics and then hopefully find a correlation between neighborhood characteristics and mental health. So yep, I live there. And typically, if we wanted to combine these 2 data sets, it'd be easy, right? We just perform an outer join on a shared characteristic and yay, we have a big data set that compiles it together, but it's actually a little more difficult. So the key question is about personal health information or PHI. And the guiding question I use is how might we merge these geolinked data sets without exposing personal health information? So these data sets don't actually have like, oh, the participant is here or they lived here, because that information is allowed to be revealed. So we had to create a new solution. So I used brute force Euclidean distance-based matching. So we have a data set of ours and a data set of mental health data. We can merge it together by computing the distance between some shared features. And we can do brute force by comparing it to every single possible census tract, which are like almost like counties in the US.
Mhm.
And then we can pick the one with the closest distance and then merge the data set on those features. A natural question from that is, what are the implications in terms of statistical confidence? So we can merge using Euclidean distance, but how do we know it's correct if we can't validate it against the real location because we can't know it? So I developed a few metrics that I won't go into detail. I developed these 5 signals that measure match quality using my Euclidean distance algorithm to inform the researcher of how confident they should be in these matches. And then I was able to create a dashboard. So hopefully we can use this outside of our team and expand it as a public tool that other researchers can use who may not have the Python experience or whatnot to do the Euclidean matching themselves. And then preparing for next semester, we have a few quick points.
Yeah, so as you can see, we developed the website. But as Tristan was saying, an important thing we want to do is link the data we created to different mental health studies. So specifically the ABCD data set, that's the one Dr. Koo is working with. So we want to be able to, in the future, actually come up with some concrete studies or concrete hypotheses that we can link and explore. So we want to do that in upcoming semesters. And then another thing we're working on is just aggregating everything we've created into one document, just sort of a write-up. So future generations of this project can see what we did and iterate on top of it. So yeah, that's our plans. And
Thank
that's
you.
our project.
Excellent presentation, guys. Yeah, really enjoyed it.